Hello, everybody. This video is about section 1.2.2 predominantly. And really, the main focus of this video is for you to understand / maybe review inverses. So remember that inverses are two equations that basically undo each other. So I really like a visual that I saw on the previous lesson. So I'm going to grab it. Here it is. So in problem 74, which was a homework problem that we did as a warm-up in class, we saw this visual where we have a value that's going into the first function, get the output, plug it into the next function, and we have a composition of functions. Now, with this problem in particular, we chose the function g to basically undo the operations of f of x. So we said that g of x in this case would be x plus 3 over 5. Now we chose this really particularly so that we have this situation where we're able to plug in a number at the top. Let's say we plug in, I don't know, 5 times 4 minus 3 becomes 20 minus 3, which is 17. And then if I plug that 17 into the next function, because I'm taking that output of f of x, and plug it into the next function, I get 17 plus 3, which is 20 divided by 4, and I'm back to 4 at the end. Now, this is how inverses work. They literally have the opposite operations in the opposite order to directly undo the other one. And so if I plug something into the top of this picture, I should end up right back where I started. So with that reminder, we started diving into examples within the book in this lesson. So this is section 1.2.2, which is related to our previous discussion about compositions of functions. So looking at problem 78, they have this scenario where we've spilled milk on the actual functions themselves, the equations. So all we're left with is the graph and this table. So using that information, do we have enough information to graph the inverse? And the answer is yes. So that's what I'm going to start with. So if we have inverse functions, you might remember from previous years or previous lessons that the x and y values are quite literally swapped. So that means I can literally take all these x values and put them in for y. So -2, -1, 0, 1, 2, 3, 4, 5. And then all the y values will go in the x spots, -6, 0, 2, 1.5, 0, -1, 0, 4.5. And now I can plot those points. So if I do so, I'll have -6, -2 at a point, 0, -1, 2, 0, 1.51, 0, 2, -1, +3, 0, 4, and 4.55. And I end up getting a curve that looks like this. So we end up having a similar shape, but it almost looks like it's been flipped on itself. And in fact, it really has. When you have inverse functions, they are a reflection over the line y equals x. So I'm going to use this ruler. And the line y equals x is where 1 equals 1, or the point 1, 1 is on the equation, 2, 2, 3, 3, 4, 4, all those coordinates that have identical x and y values, hence y equals x. So if I put this ruler right on that line, y equals x, I'm going to draw just a dashed line, or let's do a highlighted line here. So what we find is that this is a reflection over that line y equals x. If we had a problem like a parabola, or a graph like a parabola, if it was reflected over the line y equals x, it almost looked like it was turned on its side. So what are some things that we take away from this? This example reminds us that the x and the y values are swapped in the table, which means that the coordinates themselves are swapped, and that we get these graphs that are reflection over y equals x. Now, this question also asked a specific question asking, is g of x invertible? Now, this, we have to remember what invertible even means from class. And invertible is asking the question, is g of x inverse a function? So if it says, is g of x invertible, that means g inverse of x is a function. So it's not asking, can we come up with an equation? Because we can pretty much always come up with an equation for the inverse. But is that inverse equation actually a function? Which gets back to the definition of what's a function. A function is an equation or a graph where every x input has exactly one y output and no more than that. It could have 0, but it can't have more than 1. So then I got into a discussion in class about how we can picture this. And I used a parabola as an example. So let's say that we have h of x, and h of x is a parabola. H inverse of x, if it was reflected over the line y equals x, or if I swapped all the x and y coordinates, I would get a graph that looks like this. Now, we want to know, is h of x invertible? So that's the question we're focusing on. Well, first of all, let's first ask the question, which is a different question. Is h of x a function? So h of x is a function. That doesn't answer the question of whether it's invertible. It's just saying this is a fact. Now remember, to figure out if something's a function, you do the vertical line test. And the vertical line test says, if you draw a vertical line anywhere on the graph and it crosses through more than once, so like 2, 3 more times, then we know that it's not a function. So h of x is a function because it passes the vertical line test. Now let's look at its inverse. Is h of x a function? It is not a function. And that's true because if I draw a vertical line, it crosses through it 2 times in some of the locations on the graph, and many of the locations on the graph, in fact. And so we see that h of x is not a function because it doesn't pass the vertical line test. Now there's this other thing called the horizontal line test, and the horizontal line test actually looks at the original. So h inverse of x, which we use that little -1 symbol, is not a function because h of x does not pass the horizontal line test. Now the horizontal line test is, well, I recognize that this is going to be reflected. So without even looking at the inverse graph, I can tell that the inverse isn't going to be a function, because even though h of x is a function, the inverse is not, because if I draw a horizontal line, it passes through twice. So I don't necessarily have to go through those steps of drawing the inverse function to figure out whether it's invertible. So back to our original question, is h of x invertible? No. H of x has an inverse graph, but it's not a function, which means it's not invertible. So h inverse of x is not a function because it does not pass the HLT. And all of this means that h of x is not invertible. So vertical line test on any given graph says, is that particular graph you're doing the vertical line test on, is it a function? Yes or no? The horizontal line test, all it tells you is the inverse of that function a function? All right, so 78 got at a few ideas. It talked about, is this invertible? And we see that g of x is not invertible because it crosses over itself. In other words, this inverse multicolored graph does not pass the vertical line test. Or if we were to do the horizontal line test on g of x, the original, we would also see that it's not invertible. We also saw the tables, we saw the graphs, but how can we further look at inverse functions? Well, there's a couple more examples or a few more examples that I want to look at. The next one is problem 80. And problem 80 talks about, well, what if it's not invertible, but we want to be able to create 2 inverse functions using those equations? So let's look at it. So 180, this is looking at f of x equals 3 times x minus 4 squared. And I'm going to copy this graph over. So here's this graph. So this graph we can immediately see is not invertible, just like what we just talked about. It doesn't pass the horizontal line test. We know that the graph would be a parabola on its side, which wouldn't pass the vertical line test, both of which show us this is not invertible because its inverse is not a function. Now, it'd be really nice if we could restrict the domain of this graph so that we only focus on part of it, so that we have two inverse functions, even if it doesn't necessarily include the whole entire graph. So this problem gets at the idea of, what if we just focus on the positive side of this graph? Well, I guess in this side, the right side of the graph, because it's been translated. So what if we just look at this right half? Well, if we just look at that right half, we would be saying, okay, well, let's just look at f of x equals 3 times x minus 4 squared when x is greater than or equal to 4. So just starting at that vertex. Now, I chose that number really specifically because if I chose, for example, a different number, let's say I chose 2, well, then I'd be looking at parts of the graph that don't pass the horizontal line test. Well, what if I looked at starting at 3? Well, then I still am not passing the horizontal line test. Well, what if I looked at 5? Well, then I'm passing the vertical line test, but I'm really missing a nice piece of this graph that is included in the original that doesn't cause any problems. So the idea is maximizing as much of the graph as you can before it starts to overlap or fail the horizontal line test. So if that's the case, then now I can look at the inverse and it will become a function. So first, let's look at how we would find the inverse function. Remember that to find the inverse function, you swap x and y. So I swapped f of x, which is like a y, with an x, and x with a y, and then you solve for x. So my first step is to divide both sides by 3. So I get x over 3 equals y minus 4 squared. My next step is to square root both sides. I get plus or minus the square root of x over 3 equals y minus 4. And then my last step is to add 4 to both sides. I just like having my y on the left, so I put it on. Now this plus or minus, the positive part would create the top of the parabola when it's flipped, and the minus part would create the bottom part of the parabola. Now, if we restrict this domain to x values that are strictly greater than 4, then we can actually just look at the positive part of the parabola because that's the part that's getting reflected. So I end up having just this part of the graph instead of the negative part. So if I choose the inverse to be f inverse of x is equal to 4 plus the square root of x over 3 and ignore that negative part, then these two are inverses of each other and they're both functions. I've just chosen to only look at part of the graph. All right, so then two more questions. We have 81. 81 is looking at a different idea. So actually, let's look at 82 next, and then I'll do them a little bit out of order. So 82 is looking at how do you find inverse functions, which we've already done, but I want to do one more example. So let's look at 82C. We have h of x is equal to x plus 3 over 2x minus 8. And I chose this problem for the video because it is a challenging one, but we are able to find the inverse. So this is not saying to specifically find a function, it's finding just an inverse. And sometimes inverses are not functions, and that's okay. So the first step I'm going to do is I'm going to swap x and y. So I have now x equals y plus 3 over 2y minus 8. Now this one's tricky because we have two y's, and those y's tend to kind of throw us off when there's in the numerator and the denominator. So let's talk about what we can do. Well, I don't like that there's a fraction, so I'm going to multiply both sides by 2y minus 8. And I'm putting it in parentheses because I want to make sure I multiply both entire sides by the entire quantity 2y minus 8. It nicely removes the fraction from this side. And then I'm actually going to right away distribute that x because it's going to help me in the next step so that I can start getting y terms together. So the goal here is to swap x and y and solve for y. Well, I still have two y's, and right now they're on opposite sides of the equation. And in order to get y alone, they need to be on the same side. So I'm going to subtract y from both sides, removing it from the right side and bringing it to the other side. I'm also going to add 8x to the right, to both sides technically, but it's going to show up now on the right side. And I did that because I want things that have y's to be on one side and things that don't have y's to be on the other side. But I still kind of run into what feels like a problem because these y's are not easily combinable. This is where we have to go back to our roots of factoring and pull out a greatest common factor. Sometimes I use a 2 or a 3 or however many terms I need by one box to help me remember how to pull out a GCF. Because really the first step of factoring is to always pull out a greatest common factor. So I see that a y goes into both terms. Then I'd have a 2x and a -1 left over. So I'm going to rewrite this now as y times 2x minus 1. You don't necessarily have to show the step of the box, but if it helps you, use it. I like this because now I just have a single y all by itself, and now I can fully get it alone on that side. So now I'm going to divide both sides by 2x minus 1. And I have y equals 8x plus 3 over 2x minus 1. And with proper notation, I would write this as h inverse of x is equal to 8x plus 3 over 2x minus 1. So again, that process is swap x and y, get y alone, and then write the inverse notation. All right, last example. For 81, this is a slightly different idea. And this question gets at the idea of, if I have two functions, how do I know if they're inverses of each other? So I'm going to do two of them. I'm going to do 81b and c. So 81b, we have f of x is equal to the square root of x plus 2. And we have g of x is equal to x squared minus 4x plus 4. Now, in order to determine if two functions are inverses, we could graph them and see if they're a reflection over the line y equals x, but there's an algebraic way to do it as well. And so that process says that if f of g of x, oops, that's a weird looking g, let's fix that. Okay, f of g of x equals g of f of x, which equals x, then they're inverses. Well, what does that actually mean? That actually gets back to our original picture. Oops. That picture we started this video with, which says if you plug in a number into the first function, get the output, plug it into the other, and end up right back where you started, that's by definition what an inverse is. So if I plug in x in general into f of x, get an output, plug it into g, I should end up back with x, the same x I started with, which is exactly what composition of functions here is showing. If I plug in something into g and then plug that into f, and end up back to x, then I have completely undone all the operations. So let's see if that works in this case. Does f of g of x equal x? Well, the way to figure that out is to plug in g of x in for x in the other equation. So you'll notice I'm writing the square root of x plus 2, but instead of x, I'm going to put g of x, which is x squared minus 4x plus 4. Well, it's tempting at this point to be like, well, this looks gross. What am I supposed to do with that? Well, I would really like to get rid of that square root, but I can't in the form that it's in. But I can factor this. So if I were to factor x squared minus 4x plus 4, I would get x minus 2 and x minus 2, because I'd have a negative 2x here and a negative 2x here to get that negative 4x. Well, let's see what happens from here. I have the square root of x minus 2. There's two of them, so it's squared, plus 2. The square root and the square cancel each other out. And then I'm just left with x, which is exactly what I wanted. I wanted everything to cancel out. So it looks like this is likely to be a pair of inverse functions, but you do have to go both directions. So let's try it the other way. G of f of x equals I think it's going to be a lot easier to write g of x in the x minus 2 form. So that's what I'm going to do. Because it leaves just 1x instead of 2, which I like. And instead of x, I'm going to put what f of x is, which is the square root of x plus 2. I'm going to zoom in over here. All right. So that looks pretty sloppy, so I'm going to clean it up a little bit. Square root of x plus 2. All right. So this set of parentheses is not actually affecting anything, so I don't really need to include them. The plus 2 minus 2 cancel each other out, so I'm left with just the square root of x squared, which then becomes just x. So I've now shown, because both compositions ended up with x, that these are indeed inverse functions of one another. So 81b, the question asking, are they inverses? Yes. Let's look at C. C has two functions, and again, we're trying to determine, are they inverses of each other? So we have f of x is equal to 1 over x cubed, and we have g of x is equal to x cubed. So I look at those and I glance and I'm like, well, maybe they both have something related to cubic. Could they cancel each other out? Let's try it out. So f of g of x is equal to 1 over something cubed, but instead of x, I'm going to write what g of x is. But this simplifies to 1 over x to the 9th. That's not x. And so we actually don't even need to go the other way at this point, because we've already failed the composition test. And so no, these are not inverses of each other. So there's a lot of information to figure out, or like to use around inverses. So let me just show you some kind of summary slides here. So with inverses, the input of one inverse is the output of the other and results in the original input. In other words, if I plug something into the first function, take that output, plug it into the other, I'll end up right back where I started. Not all inverses are invertible, meaning we can get an inverse, but it's only invertible. No, inverse, yeah. It's only invertible if the inverse is a function. If you use the horizontal line test on the original, you can tell if the inverse is a function or not. Inverse graphs are reflected over the line y equals x. We just showed that the compositions have to simplify to x for it to be an inverse. And it's a good way to verify. If we want to solve for an inverse equation, we just swap x and y and then solve for y. For tables, we saw that we could swap the x and the y's just like the coordinate, and that the proper notation for inverses is to do the name of the function f of x or g of x or h of x with that -1 raised in the, it looks like an exponent, it's not an exponent, but raised high in between the f and the x. And that's a good summary of inverses.